Welcome back to My Favorite Universe. In this, Lecture 9, we're going to do something special. I'm going to present to you what I'd like to call the greatest story ever told. And in it, I have the privilege of synthesizing for you the greatest discoveries of physics, of astrophysics, chemistry, and biology, and present to you a coherent story of the cosmos from the earliest times right up to the present. We're not the first to have wondered about cosmic evolution. Go back to Lucretius. He says here, the world has persisted many a long year, having once been set going in the appropriate motions. From these, everything else follows. How prescient that quote was, given how long ago it was written. To realize that the universe is a describable place, and that the universe, using the methods and tools of science, allows us to determine how it was born, how it evolved, and where it will go in the future. Before I begin this story, the greatest story ever told, I want to first describe a famous equation. An equation, I think it's the first equation we all learn in elementary school. It's E equals mc squared. We learn that equation before we even know what it means. We know it has something to do with Einstein. Well, it has a lot to do with the birth of the universe. Let me remind you, if you once knew, and tell you for the first time, if you've never known, that if you have particles, take a proton, for example, you can actually ask the question, what is the energy equivalent of the mass of that proton? That's a perfectly legitimate question. And you know how much energy is contained in that proton? Plug it into that equation and find out. Plug in the mass on one side, multiply it by the speed of light squared, that's the c. And out on the other side, you find out if you converted that proton into energy, that's how much energy you're going to get. It works in the reverse. If you have a concentration of energy, and you want to ask, what kinds of particles can I make with this energy? Go look up on the table and find out which particle has about the same energy equivalent as the energy I have. Then I can make that particle. And so this two-way street that exists between matter and energy, as described by E equals mc squared, is rampant in the early universe. It's rampant in particle accelerators. You just hardly ever see it at home, or in the street, or on the sidewalk, or in the park. So let us begin, now armed with that important piece of physics. Where else shall we begin but in the beginning? How long ago? Some 12 to 14 billion years ago. All the space and all the matter and all the energy of the known universe was contained in a volume less than 1/trillionth the size of the point of a pin. The point of a pin. And that size is about the size of an atom. So imagine the entire cosmos compressed down to something that small. Conditions were so hot that the basic forces of nature that collectively describe the universe, they were unified. They were one. The unification of forces is not a new concept. In the 1800s, electricity was known as a force, as too was magnetism. Until later in the 19th century, it was revealed that, in fact, electricity and magnetism were two sides of the same coin. There was a theoretical formalism that enabled you to look at those two forces as the same thing, manifested in different ways, just depending on the circumstance. That was the first time two forces were unified. Electricity and magnetism becoming electromagnetism. That's an example of a unified force. We have reason to believe that all the known forces of nature were unified in these early times in the cosmos. Now, for reasons unknown, this pinpoint cosmos began to expand rapidly. When the universe was a rather warm million, trillion degrees, and a rather young 110 million, trillionth of a second old, before which all of our theories break down, and we have no clue what was possibly happening in the universe before that time. Black holes were spontaneously forming and disappearing out of the energy contained in that unified field. The energy density was so high that it wasn't just making particles switching back and forth on this two-way street between matter and energy. It was making entire black holes. And black holes, as you know from an earlier lecture, as you know, black holes, as described by Einstein, are the curvature of space and time. The fabric of the universe is reacting to the presence of black holes. And if you have black holes forming and unforming spontaneously in the early universe, all contained in a... And we have a term for it. We call it quantum foam. The quantum foam. Now, during that period, a fascinating thing was happening. The subject of quantum mechanics, discovered and invented in the 1920s to describe matter on its smallest scales, and general relativity, the modern theory of gravity put forth by Einstein, describing the nature of the entire cosmos, those two theories do not intersect. They operate on completely different domains of the cosmos. One is the smallest, one is the largest. And we're worried about that because you can't look at one theory and infer the existence of the other, yet they both accurately describe the cosmos. We worry about it because how can two things that don't know about each other be simultaneously true in the same universe? So we're working on that. But what we know is that there was, back in the early times of the cosmos, the whole universe was small. So we have this kind of shotgun wedding between quantum mechanics and general relativity. They can't avoid looking like each other because I got the whole universe down to the size of an atom. I got an atom containing the entire universe. Quantum mechanics and gravity were one. They had to be. There's nothing else they could have been but one under those conditions. And as the universe continued to expand and cool from those times, gravity splits away from the other forces of nature. Gravity splits away. As forces split from each other, they begin to occupy the domains in which we have come to know that they matter. So gravity splits away. Gravity starts looking like a force unto itself, with no identity shared with the other forces. And that's fine. Let's keep going. Quickly after that, the strong nuclear force and the electroweak force split from one another. What happened then? We believe that was accompanied by an enormous release of stored energy. Energy that was stored in the merged fields. You split these fields, energy gets released. So much energy that it forced a 30 power of 10 expansion on the size of the universe. Of rapid expansion. In fact, we call that the epoch of inflation. This release of stored energy is not unlike the latent heat of freezing that you may have remembered from your chemistry class. It's very much like that. Where if you have water and you watch you put it in the freezer and you watch the temperature of the water drop, there's a point where the temperature stops dropping because it's now converting itself into ice. Then when it's completely ice, the temperature drops again. Well, what was going on in there? You're trying to take heat out of the system, and how come the temperature didn't continue to drop throughout the time it was becoming ice? Because there's a latent heat in the liquid form of that water that is not there in the solid form of that water. That latent heat got released into the environment. No, making ice cubes doesn't make the universe expand, but when you're splitting forces in the early universe, you have the kind of energy that does impose itself on the structure of the cosmos. This rapid expansion stretched the cosmos. Much of the variation in density and structure and form of the universe, if you stretch it by 30 powers of 10, whatever might have been a heavy fluctuation in the early days becomes softened. And we measured this. we measured this. And that smoothing of the universe is now down to 1 part in 100,000. How smooth is that? Well, imagine a 2-mile wide lake, and you put a ripple in that lake. Ripples in the lake. How big should the ripple be compared to the size of the lake? The ripple be an inch tall, an inch, on a 2-mile wide lake. That's a fluctuation of 1 in 100,000. We'll get back to those fluctuations, but it turns out to be significant because it's in those fluctuations where ultimately matter, once it finally forms, will coalesce. And when we look at the large-scale structure of the universe and ask, where are all the galaxies, we're going to find those galaxies where those ripples were. So the imprint of what the later structure of the cosmos will be is being shaped in this time. Continuing onward with now what is laboratory-confirmed physics, rather than the theoretical speculation that has come before this. The universe was hot enough for photons, now particles of light, photons, particles of light, to spontaneously convert their energy into matter-antimatter pairs. In fact, light loves to do that when it has enough energy. What are matter-antimatter pairs? It'll make a proton and an antiproton. It'll make a neutron and an antineutron. Pick your particle, it'll make the matter-antimatter pairs. By the way, antimatter is real. It was all over the early universe. We make it in particle accelerators. It's not just an invention of science fiction. It is real. It's just not familiar in everyday life. It's not often you have an encounter with antimatter. If you did, it would be your last encounter. So this interplay between the photon that has so much energy can start spawning particles, and the particles, you have matter and antimatter pairs, you know what happens if they get together, they form the photon again. They annihilate. So we have a two-way street going back and forth. It's a soup, a matter-antimatter photon soup. Once again, invoking E equals mc squared to make that happen. For reasons unknown, the symmetry between matter and antimatter in these conversions was broken. Broken. And this is profound. We don't know why that symmetry was broken, but it was broken. And what that meant was 1 out of a billion photons that would normally convert itself into a pair made just a matter particle without the antimatter counterpart. It's a broken symmetry. So in other words, for every billion matter-antimatter particles on this two-way street, there's one matter particle that has no mate. The symmetry was broken. And as the universe continued to cool, the matter-antimatter got together. It's like a square dance. You match it, you pair up with people, and if you're the odd one out, everyone else is paired up, and you're left over. You're left over. These matter-antimatter pairs made photons. The photons continued to cool. They dropped below the energy level to make particles. So we just froze out some photons from what was formerly a two-way street, got rid of the 100 billion paired matter-antimatter particles, and what are you left with in the end? You're left with a matter particle and 100 billion photons. Excuse me, a billion photons. And it's these matter particles that are responsible for all the structure. In modern day, they revealed as 4 separate forces, having started as one in the early universe. There's the strong force, already mentioned. That force binds particles in the nucleus of the atom. Protons, they have positive charges and are sitting next to each other in atomic nuclei. How's that even possible? Light charges are supposed to repel. In fact, they do repel. Unless they get close enough, the strong force takes over. That's why we call it a strong force. It's stronger than their tendency to want to repel each other. Strong force keeps nuclei together. The weak nuclear force is responsible for the decay of atomic nuclei. There's a third force, electromagnetism. Like I said, back in the 1900s, they were two separate forces, where they're now one. One force even in our own lives. Electromagnetism is revealed in that which keeps matter together. Matter. The bonding of atoms. Human flesh, wood, carpet, it doesn't matter. Stuff that's in our everyday lives that's bound together by electromagnetic forces. And the fourth of those, the one that has the largest range, the one that has the greatest impact on the events of the cosmos, is gravity. So while the energy of the photon continued to drop, energy of the universe, it stops. It stops. It'll still happen, but in very restricted places, like the centers of stars. So we move on. "300,000 years after the Big Bang, the universe continues to cool. Right now, we went from those very high temperatures. The temperature now is about 2,000, 3,000 degrees Kelvin. Up until then, protons and neutrons had combined and made the lightest elements on the periodic table. They made hydrogen, helium, and even lithium. But the electrons were free to roam. It was not cool enough yet for an electron to settle down into the atom. So we had nuclei flying around and protons and electrons flying around. Turns out light likes electrons. If an electron sees a photon of light, it'll bat it back and forth. They interact with each other, so they scatter the light. So light did not have a free trip through the universe. It was kind of like a random walk, like a pinball moving through a pinball machine. So before 300,000 years, the universe was opaque. Our telescopes today cannot see through that wall of light, like the frosted glass in a bathroom window. But at 300,000 years, the temperature drops to a couple of thousand degrees. That's cool enough for electrons to be bound to the atoms. The universe becomes transparent. And all of the photons left over from that period, they're still in the universe. But as the universe has expanded, they have continued to cool. And what then was a temperature represented as 2,000 or 3,000 degrees, the universe is now 1,000 times bigger than it was back then. And it's a linear relationship between the two. Right now, the temperature of the universe is 3 degrees. We went from 3,000 to 3 degrees Kelvin. That's what it is today. That's the famous microwave background. Because a 2,000 degree object actually radiates infrared and visible light. You can see that. But if it's 3 degrees, it's not visible to the human eye. But it is to a microwave receiver. And it's everywhere. So we call it the cosmic. First few billion years, galaxies were manufactured. The Milky Way was one of them. Our Milky Way was one of them. How many galaxies were made? Somewhere between 50 and 100 billion galaxies, each containing up to 100 billion stars. Each of those stars undergoing thermonuclear fusion in their cores. They're stars that with more than about 10 times the mass of the sun. They're very special in the evolution of the universe, because they have enough mass to create enough pressure, to create enough temperature, to turn their cores into a factory, an element factory. They manufacture dozens of elements over their lifetime, beyond the birth elements from the Big Bang, beyond hydrogen and helium and a little bit of lithium. These stars make the elements that we are composed of. They make the carbon and the nitrogen and the oxygen and the iron. They undergo thermonuclear fusion to do that. Thermo uses heat. Nuclear, what are you doing with the nucleus? Fusion, you're bringing them together. The anatomy of that word. Actually, so what if the star just made the elements? They're no good inside the star. We got to get them out of the star somehow. Turns out those stars explode. They blow their guts to smithereens in the galaxy. At the end of their lives, that's how they die. They're visible. We see them. We call them supernovae. So fortunately, their chemical enrichment is now returned. Not returned, it was manufactured there for the first time and is now distributed across the galaxy. In fact, the universe might view it as pollution. But since we're made of the stuff, I think of it as enrichment. Now, after 7 or 8 billion years of this enrichment, in every galaxy, but in particular the Milky Way galaxy, an undistinguished star, the Sun, was born in an undistinguished region, the Orion arm, of an undistinguished galaxy, the Milky Way, in an undistinguished part of the universe, the Virgo supercluster of galaxies. I like to think of that as your cosmic address. It's what you put on an envelope if you wanted to mail something to another, mail a letter to someone else in another galaxy, in another part of the universe. The gas cloud that made the Sun had a big enough supply of heavy elements that it spawned a system of planets, 10,000 asteroids, trillions of comets. While most of the universe is hydrogen and helium, everything else on the periodic table is what you really need to flesh out the rest of what the universe is about. You don't make planets with just hydrogen and helium. You need the rest of the ingredients as well. Make rocks and people and oceans. The early part of the Earth spent 600 million years suffering the bombardment of debris left over from the formation of the solar system. And every time an asteroid hits, it heats up the area where it hits. If you are a molecule trying to become something ambitious, you get destroyed. And if you're hit often enough, you raise the temperature of the entire surface of the Earth until you're basically sterilized. So for 600 million years in the early history of the Earth, nothing could form, even though it had the 800 million years of it. That's enough. It begins to subside, Earth's surface cools, we start making complex molecules. Complex molecules. What else is important to life? Liquid water is important to life. Where did Earth form? No, it didn't form too close to the Sun. Otherwise, all our water would have evaporated. It didn't form too far away from the Sun. Otherwise, all the water would have frozen. There's a zone, a nice habitable zone, where Earth was formed. So now we have the right temperature. Think of that as the Goldilocks effect. We've got the right ingredients, and the temperature has subsided after the end of the bombardment, period of bombardment, so that now we can do some interesting things. Within the chemically rich liquid that was our oceans, by mechanisms still to be learned in the community of biologists, life began from organic matter. Organic non-life became organic life. That time took about 200 million years. From the end of the period of heavy bombardment to the point of our oldest fossils, 3.8 billion years ago. So we start out with a 4.6 billion year old Earth. 600 million years goes by. We're at 4 billion years. Heavy bombardment ends. 200 million years go by. Life begins. This early life, it was single-celled organisms. They weren't doing calculus. They had very simple lives. There was no oxygen, so they were anaerobic. They thrived in the carbon dioxide-rich atmosphere of the Earth. As a waste product, they released oxygen. In fact, they ultimately died in their own excrement, this oxygen. Oxygen is very bad for you if you are anaerobic, but it's very good if you are aerobic. And it enabled a whole generation, a whole population of the Earth to take over that was full of aerobic creatures, thriving on the oxygen made by the previous generations of single-celled organisms. oxygen in the oceans as well as in the atmosphere. That oxygen not only enables aerobic life, that's O2 in the atmosphere. There's another version of oxygen, O3, we call that ozone. That was formed as well. It gets to rise up in the atmosphere and protect us from the ultraviolet radiation from the sun. Ultraviolet photons have enough energy to break apart molecules. It's hostile to life. It's hostile to the stability of life. So we simultaneously get air to breathe, an oxygen metabolism, and protection from solar UV radiation. We owe the remarkable diversity of life on Earth to something profound. That among all the elements that are in us, there's one that's quite special, and it's the element carbon. Carbon is plentiful in the universe, made and manufactured in these crucibles in the centers of stars, spread into the galaxy. Carbon, you can make more kinds of molecules with carbon than you can with all other elements combined. It is a fertile element with which to make your experiments on life. And you look at the diversity of life on Earth, and you say there's only one element that could have been responsible for that, and that's carbon. We are carbon-based life. But life is fragile. Life is fragile. Not as often as it once did, but it still happens. Asteroids come and slam into Earth, completely changing the ecosystem, if only briefly. 65 million years ago, a 10-kilometer asteroid came and slammed into the tip of what is now Mexico, the Yucatan Peninsula. Made a 200-kilometer diameter crater. If you were there, you were vaporized. If you're on the other side of the Earth, the trillions of tons of Earth's crust that was thrust into the stratosphere cloaked the Earth, blocked sunlight, took out the base of the food chain, and if you didn't die from the impact, you died because you starved. 70% of all species of life on Earth's surface went extinct at that moment, including the classical dinosaurs that we've come to know and love and respect from afar, like T-Rex. Some animals survived. There was a tree shrew running up and down trees and underfoot, trying to not get eaten by T-Rex. That spawned all the mammals that followed because tree shrews survived that collision. It pried open a whole ecological niche that was not previously available to the tree shrew. They didn't have T-Rex chasing after them, turning them into appetizers. And so, one branch of these mammals became primates. One branch of those primates became Homo sapiens, these big-brained things that have what we call intelligence. And that intelligence enabled Homo sapiens to invent methods and tools of science, to invent astrophysicists, and to deduce the origin and evolution of the universe. Yes, the universe had a beginning. Yes, the universe continues to evolve. And yes, every one of our body's atoms is traceable to the Big Bang and to the thermonuclear fusion that went on in the center of a high-mass star that gave its life to us. We're not simply in the universe, we are part of it. We are born from it. One might even say that we've been empowered by the universe to figure itself out. And we've only just begun.